Okay, in section 1.3, we're going to talk about radicals. And when we're talking radicals, we're talking things like this, where you have a square root symbol. So the symbol we use for this is called a radical sign. The thing inside, if you're going to talk about it, you could call it either the argument or the radicand. Anytime you have a value inside of a function, and this isn't necessarily going to be a function because it depends how we define the answer, but often we'll call that an expression. The whole thing is an expression, so we may as well put the term radical in front of that. Radical expression, or an expression. Again, sometimes the argument, the thing on the inside. Okay. Now when I do something like take the square root of 4, if we think what factors can create 4, what two factors exactly the same, if we multiply them together, create 4. So when I take the square root of 4, what I'm saying is, what's one of these? So 2 is an answer. But there's another answer to this, because 2 times 2 equals 4. There's another answer to this. The second answer is really minus 2, because minus 2 times minus 2 equals positive 4. But, and this is often the case with science, the positive version we call the principal root. And sometimes your software is designed only to deliver the principal root. Like if you use your calculator and you take the square root of 4, it's only going to give you one number. It's going to give you 2. It gives you the principal root. So keep in mind, though, that minus 2 is another solution to this. And we're going to see that sometimes we have to consider more than just the principal root in future lectures. Okay, so let's talk about products and quotients of radicals. Scoop this up a little bit. So say you have, in general, if you take, say, the square root or any radical of a product of two numbers, that's the same thing as taking the product of each radical individually. So you can split those up like that. Conversely, if you take the root of a over b, this is the same thing as the root of a over the square root of b. Square root in this case. And the reason I say square root is because the square root, say, of 4 can also be written as the second root of 4. Normally we just take, when we're dealing with just the square root of something, we just ignore this 2 and we leave it off. But we could also do say the third root of 8. That means with 8, what's the number that if you multiply it by itself 3 times gives you 8? So the cube root of 8 is 2. Now notice in this case, it is just a single value because minus 2 times minus 2 times minus 2, that actually equals minus 8. So cube root of minus 8 actually equals minus 2. So these are different things. And you can have any number up here in your radical. You could have the fifth root of, say, 32. The fifth root of 32, start writing, is actually 2, because 2 times 2 times 2 times 2 times 2 equals 32. Count it up yourself. So that's how that works. So how about adding and subtracting? Say you have the square root of 2 plus the square root of 8. How does this work? Well, you can't add roots unless they're the exact same root, like for example square roots. So here we got square root of 2 plus square root of 2. This means we would have 2 square root of 2's. I could have the cube root of 2 plus the square root of 2. We can't do it. We can't do it. I can't add the cube root of 2 and the square root of 2. Not directly like that. Now I could calculate what this is. I could calculate this value, and I could calculate this value. So we could figure out what cube root of 2 is, which is 1/3, and the square root of 2 is 1.14, goes on forever, and then we could add those two numbers together, which we get approximately 1.474. However, when we add these radicals directly, you can only add radicals directly if the radicand and the argument are the same. So these are both square roots, so that's the first case, and we have both 2's here. That's the second case. So we can add these together. So in this situation, we can't add those, but we can recognize that this is the same thing as square root of 2 plus the square root of 4 times 2. And as we said before, we can split that up. So this is the square root of 2 plus the square root of 4 times the square root of 2 equals the square root of 2 plus, well, the square root of 4, the principal root, let's just say, is 2 times the square root of 2. So up here, this is square root of 2 plus essentially 1 times the square root of 2. Now down here we've got square root of 2 plus 2 times the square root of 2. So this is actually going to be 3 square root of 2. And if you go and you stick square root of 2 plus square root of 8 in your calculator, you get approximately 4.24, and it goes on forever. And if you take 3 times the square root of 2, put it in your calculator, you get approximately 4.24. So we just double check that this works. Okay, another thing that you want to consider is one thing, we don't like to see radicals in the denominator. I mean, you can do it, but it's not pretty enough. So really what we want to do is get rid of that in the denominator. So how do you get rid of something like that in the denominator? Well, if we multiply it by itself again, then in the denominator, square root of 3 times square root of 3 is just going to be 3, right? But if I multiply the denominator by that, I'm going to change my equation. So I have to keep the equation the same. I have to also multiply the numerator. So I have square root over 3 over 3, which is essentially equal to 1. So I'm not changing this. I'm not changing this orange expression at all. So now I have 7 square root of 3 in the numerator total. That's That's the way it should look. So when you're simplifying your radicals, you might want to keep that in mind. So we can write our radicals as exponents. Suppose I have the square root of some value a, or let's call it the nth root. We can put any value in there, 2, 3, 4, 5. We can rewrite that as a to the 1 over n, the fraction. Why does that work? Well, think about it this way. Suppose I have the square root of 4, and I'm saying this equals, I'm saying this equals 4 to the 1/2, or 2. So if I multiply it by itself, 2 times 2 equals 4. That's really kind of what we're saying here. So the square root of 4 equals 2, but I can write it as 4 to the 1/2. So if I take 2 of these, like I'm doing here, actually I don't want to do it there because I don't want this equal sign here to represent. So this equals that, but let's say I go 4 to the 1/2 times 4 to the 1/2. Well, if we remember our exponent mathematics, that's the same thing as saying 4 to the 1/2 plus 1/2 equals 4 to the 1. So you can see this is the same as this. So this radical sign is a symbol. Radical sign is a symbol. But if you're gonna be doing lots of mathematics, you really want to convert everything into an exponent because it's a lot easier to work with. Because you might have more operations going on, and for example, you could have something like a to the cube root of a. But then you want to square this. Well, what does this equal? Looking at it in the symbol like this, it can be a little tricky to see what that represents. But if you keep in mind that really what we're talking about is a to the 1/3 squared, well, now if we remember our operations on exponents, now this is the same thing as saying a to the 1/3 times 2, or a to the 2/3. So that's much simpler, and it's more compact and much more easy to use than the symbol. And on that note, we'll end this discussion in section 1.3 on radicals.